In the last lecture, we talked about complexity. We talked about different classes of complexity, and we talked about the idea that there could be different computations, different algorithms to accomplish the same task, and we'd always like it to be the case that we have a really efficient one. One question you could ask is, so how do you find, or how do you create, or how do you invent an efficient algorithm? And the answer is, it's hard. Many great computer scientists go through their entire career with perhaps one classic example of a great algorithm that is used regularly. Many don't come up with any. And that's okay, because often it's easier just to reduce a problem to a set of known solutions. Somebody's come up with a great algorithm. How do I take a new problem and reduce it to something that can take advantage of that algorithm? And so that's, in fact, often what we want to do, is we want to understand what's the inherent complexity of a problem, and then think about how to break a problem down into subproblems, which we can then relate to other problems for which there already exist efficient algorithms. If we can rely on a great algorithm from somebody else, we're going to use it. So we're going to look at an example of that, and we're going to look at it in the category of dealing with search algorithms. So what's a search algorithm? It's a method for finding an item or a group of items with specific properties within a collection of items. It might be a list, and I want to find things that belong in that list in particular properties. It might be a set of other things that are not structured in the same way. Basically, I've got a collection of items, which I call the search space, and I want to look at how do I very efficiently find out something inside of that search space. We've already seen examples of this. For example, finding square roots. We saw this as a search problem. We could do it with exhaustive enumeration, where we looked at every possible element from the search space. We saw bisection search, where we cut down the problem in half each time. We saw Newton-Raphson. These are all examples of search problems. And what we'd like to do now is to talk about, so in general, how do we do search? And what's your inherent complexity associated with doing search? Well, let's begin, first of all, with just a simple way of doing search. Just linear search. Really simple method would say, gee, given a collection or a list, I'm going to assume it's a list, but it could be something else, but given a list and given some element, I want to know, is that element in the list? And what could I do? Well, I could simply walk down the list, one element at a time, testing it. So I'd do a little for loop that goes through the entire length of the list, checking to see for each element in the list, is it the thing I'm looking for? When I find it, I return true. If I get to the end of the list, I return false. Okay, simple method. And you already know what the complexity is here, or should be able to guess it. If the element's not in the list, I'm going to have to go through the number of tests equal to the length of the list. So the complexity is the order of the length of the list. I might stop a little earlier if I actually find it, but we're always interested in the worst case behavior, and so at best, this is linear in the length of L. At best. Wait a minute. Why do I say at best? Well, in fact, I'm making an assumption. And the assumption is that each test in that loop can be done in constant time. Wait a minute. We already said we're going to make assumptions about operations inside of the machine being constant. But notice here, I'm making a specific assumption, which is, remember, that test is to go to the ith element of the list, extract it, and then do the comparison. Comparison is certainly constant in time. But is it really the case that I could get to the ith element of a list in constant time? Does Python retrieve elements of the list in constant time? Well, let's look at that. The answer, by the way, is yes, but let's look at why. So let's look at a simple case. Imagine my list is just a list of integers. So each element is of the same size. For example, it might be 4 units of memory, or 4 8-bit bytes. We won't worry about the details of how it's stored, but we might say, okay, I'm going to take 4 pieces of memory, stitch them together, and that's the size of each one of my elements. If that's the case, then the address in memory of the ith element is easy to find. If this is my memory, and right here, that's where the list starts. So start points to that element in memory. Then, if I'm breaking up my memory into 4 units at a time, then the ith element, the location of it, I can actually compute. I want to know how to get to start, and then I want to take 4 times I to get out to the location of the ith element. So start gets me to here, and adding 4i gets me up to that element. I can basically compute exactly where to go to get to the beginning of the ith element. And if I can do that, then I know in constant time what the location of the ith element is, Therefore, in constant time, I can get it, and I can retrieve it and do the comparison. In other words, it says if I want to get to the ith element of a list of ints, I don't have to walk down the list one at a time counting. I can actually compute exactly where to go to get to it. Great. Well, wait a minute. That works when I know that the size of each element is a particular size. I can allocate a specific amount of memory for each one. But what if the list of objects are things that have arbitrary size? Now what do I do? And in this case, I use a wonderful tool called indirection. Here inside of Python, I'm going to represent a list as two things. A length, telling me how many objects there are in the list, so I know where the end of the list is, and then a sequence of fixed size pointers to objects. Or another way of saying it is, inside of the list, each element of the list isn't going to be the element itself. It's going to be a pointer to an object, a pointer to a structure in memory. And if I can do that, then in fact, I can still get to any element in constant time. Let's see why. If the length field is just 4 units of memory, in other words, I need 4 units of memory to tell me how long something is, and each pointer occupies 4 units of memory, so similar to before, the address to anything in memory can be done in 4 units of memory, then in fact, I can get to the address, or rather can compute the address of the ith element very easily. I take start, which tells me the beginning point. I add in 4 to get past the thing that tells me how long the list is. And then, as before, I take I times 4 to tell me the location of the pointer to the memory. This address I can compute in constant time. The value stored there is a pointer to another location in memory, and that can also be found in constant time. So the whole search is linear. It's called indirection because I determine where's the point in the list I want to go to in constant time. Getting there, what I take out isn't the value itself, but it's a pointer to another location in memory. And I can go there in constant time and pull it out. It takes 2 steps, but that's still constant time. And so the search in this case is in fact linear. I can get to any point in a list in constant time, and I have to go through the entire list once. So the entire search is linear, which is what we knew. And this idea of indirection is exactly what makes it happen. It says that I can access something by first accessing something else that contains a reference to the thing being sought. In this case, I'll represent a list as a list of pointers to objects rather than the objects themselves. Okay, so I got a simple linear search.